It's the best. D, option 1, option 2, this or that. No other options available. So that's going to have to be the first rule that's met. There needs to be like a success or not a success. Success, failure, whatever. Okay, so you can't have 3 or 4 or 5 or 6 outcomes. You can only have 2. And they have to be mutually exclusive, meaning there's no intersection. Can't be both at once. It can only be one or the other. Rule number 2, there has to be a fixed number of trials that you are doing with these binomial distributions. So this n has to be defined. How many times are you running the experiment, or how many times are you doing the probabilities? It's 6, 12, 26, 500, doesn't matter the number, but it has to be fixed. Okay, Kate can't come by and change it later because she wants to. And number 3, the final rule is the probability of each trial has to result in the same success rate. Thank you, sir. Meaning every time I go to do my trial, the percent chance of success versus failure or whatever has to be the same. So these are all pretty much independent events. So something on the first event can't change the sequential ones afterwards. They all need to be the same. So we're going to test this on a few examples. You don't have to do this every time you do one of these problems, because I'm just going to come out and say on most of them, hey, this is a binomial distribution. Then you're going to know all 3 of these apply. The binomial random variable x. Remember last class we had to define what x is? On this one, it's always the same, so you don't have to. X is defined as the number of successes out of your fixed number of trials. That's what x is going to represent on this distribution. Last class we talked about, Matthew had to write x is equal to number of heads on the coin. X is equal to number of times whatever. Okay, he had to define his x on those homework assignments. Here, x is always going to be defined as the number of successes out of our fixed number of trials. So the kind of questions we're going to look at today are going to be like, if I do something this many times, what's the probability that I get this many successes out of it? That's the type of questions we're going to be looking at. So for those of you guys that are like in the medical field or thinking about doing that, this kind of stuff is more useful to you, because you want to know, if I see, 15 whatevers, what's the chances of 3 of them are going to have this condition? If the percentage chance of people having it is this. So do I need to be worried, or is it not that big a deal? All right, so let's decide, are these 3 scenarios binomial distributions or not? So we have to go through and check, do all 3 rules get met? So number 1, I'm going to toss the coin 10 times, and I'm going to count the number of heads that I get when I flip the coin 10 times. So rule number 1 says each trial results in one of 2 mutually exclusive outcomes. Would doing this experiment or trial give me only one of 2 options? Yeah, either it's heads or tails, and you can't be both, so they are exclusive. So rule number 1's met. Number 2, are there a fixed number of trials that I'm going to run in this particular experiment? Yes, it's telling me I'm going to flip it 10 times. So number 2's met. Rule number 3, is the probability of each trial the same? Yes, every time I flip the coin, what's my percentage chance of heads versus tails? 50-50 in this particular case. It doesn't always have to be 50-50, but in this case it is. So the 10th flip or the first flip, the percentage will remain the same. So this is a binomial distribution. We're good here. Again, you don't have to do this every time you do the problems. I'm not trying to make it look like you got to write a paper and then you can do the problem. You're going to know all of these are true because we're just going to be working on these types of things. But in the back of your mind, know that these conditions have been met. Number 2, I'm dealing 10 cards from a shuffled deck and I count the number of red cards. Are there only one of 2 mutually exclusive outcomes on this one? Just red or black, right? Unless I'm playing Uno or something weird. We're just going to pretend it's a standard deck. It's either red or it's black. So we're good there. Number 2, is there a fixed set of number of trials that I'm going to run on this one? Yeah, I'm going to run 10. So far, so good. Here's where it trips us up, though. Number 3, the probability that a trial results in success for all the same success for all the trials. Is that true? No, because once somebody gets a red or a black card, what happens to the rest of the probabilities? They all change either more or less. Exactly right. So this fails to be a binomial distribution because the probability does not remain constant throughout the whole process. Kind of see the difference now? All right, last one. We got 2 parents with genes for O and A blood types, and we want to count the number of children with blood type O. So do we have 2 mutually exclusive outcomes on this one? I mean, I guess for the most part we do. I'm not a blood expert, but if you only have 2, I guess you can only have 2. I don't know. There's other ones, but I don't know if your parents only have these. Is it possible to? Yeah, that's what I thought. So we already know it's kind of sketch before we do bond. It's not going to pass, but we could say for better reasons than this. But we'll just say for the purposes of this problem, there is one of two. So, okay. But Lauren's right. I've heard of people that have like 2 O-type bloods having a kid with like AB negative out of nowhere. Does this have a fixed set of trials that I'm going to run? No, and that's where it fails. We're not gonna say that the family can only have 3 kids. They can have as many kids or as few kids as they want. So that's really where this one fails. But Lauren, like me, earlier in class, I always tell people, I think it's 5th or 0 period. Like she said, there's anomalies. You know, you're gonna have maybe the kid's not really yours. No, I'm just kidding. Mr. G's joking. It's Friday. I joked about that both times my kids were born. My wife was not too pleased. Because they always hand to dad, all right? So future dads, if there's any potential ones in the room, I'm not saying start now, but just in the future, they do hand you a packet with all the stuff you're supposed to fill out for your new child. And first page on there says, do you wish to request a DNA test? Like you don't have to ask mama's permission. You can sign on one of those things. So I joked, I was like, you know, every time I was like, do I need to do this? She's like, stop it. You know, so my son ends up looking. No, I know, but that's me. This is why I get into trouble. This is just how I live life. I always like, you know, I do stupid things. Yeah, she's all like, if she could hit me, she would have. But my son, he looks just like me. But my daughter, I often question because she's the only left-handed person in the family. And my wife's like, but no, she thinks just like you do. I'm like, I know, but I think it's because I trained her that way, not because of my DNA. Anyway, so just, you know, just as a joke, just because it's Friday, we can relax a bit. Okay, so we know what the 3 rules are going to be for, and half you guys know who my wife is. You can ask her about that story. She'll probably be like, this is why I don't like my husband sometimes. So we know that the 3 rules have to apply for it to be binomial. Now we're going to look at, okay, how do we solve these types of questions? So as always, you guys know my routine in class. Now we're going to do it the long way first, just so you guys can kind of see how it works. And then again, this little blessed device of technology, we're going to press like 3 buttons, and our answers will be given to us from the magical fairies that do math. So if you need a calculator, grab one. The formulas are on your chart. It says if X has a binomial distribution, which you will know, okay, unless I'm trying to get Matthew to figure it out, he's going to know beforehand that he has a binomial distribution, then this formula right here is the one you use to find your probability if the value you're looking for equals exactly this. All right, so all of these weird letters and words have meanings. I'm going to write them down on my paper as we talk through these, and then we'll do a few of them again on the camera so you guys can see. I like the slides. I think they do okay, but the problem is they don't always show the steps. And I think it helps you guys to kind of see how I got from A to B instead of just jumping right there. So there's a couple letters on here to pay attention to. The first part here, this is your probability statement. You will have to write this regardless of how you solve these to let me know what you're solving for. But this probability that X equals K, or on your notes, it's a lowercase x, whatever you want to use, it's just a placeholder. That's what you're trying to solve. Okay, so if I'm flipping the coin 10 times, like we said on our last example, and I want to know the chances of me flipping exactly 3 heads, which hint is going to be our number here that we're going to do in a second, then I would write P parentheses X equal to 3. I want to know the probability that X is 3. That's my success rate. And so when you scroll over here and kind of look at the right side, this is where you start filling in your information so you can actually get an answer from the calculator. We've not used this notation before, this parentheses N over K or N over whatever. You'll see it as N over R in some of your college classes if you guys take stats again. Basically, it's just telling you you're doing a combination there. Because whenever you're looking for success out of a group, there's more than one way to do it. So you have to go back to what we talked about in, what was that, like November, December, where we did the permutations, the combinations, and we said order matters, order doesn't matter, that kind of stuff. You have to do one of those here because there's more than one way to get 3 heads out of 10 coins. So we're going to mathematically add up all those combinations without having to do a tree diagram or anything, and then multiply that answer by the actual probability of one of those events happening, which is this part right here. So the letter N is going to be your number of trials that are going to be given to you in the problem. So it's going to say we flipped the coin 10 times, we talked to 12 babies or whatever. Your number of trials is your N. The letter K on the screen or the little letter X on your notes is going to be the number of successes that you want. So that's the one you're trying to find out about. S-U-C-C-E-S, okay. And then what else we got on here? The letter P is your percentage or your success rate. And did I cover everything? Yes, that should cover everything. So when you look at your formula, I'm going to write it down like it looks on your notes so you guys can see it here on my camera when I turn it on. Basically, we just need to plug things into this formula, multiply them into the calculator, and then life will be all nice and golden. And then after we do it the hard way this couple times, I'll show you guys that you don't even have to mess with it anymore at all. This way you can just go straight into the little program that we have. Okay, so I wrote down what all your little letters stand for. Here's your formula. And remember, this little thing just means you're going to take whatever your number of trials are, C, and then X. And so that function, if you forgot, is in the calculator. And that's math, probability, and that's number 3 right there. So we're going to use that. Okay, so let's look at the first example. It says, example number 1 in your notes. Out of 3 coins that are tossed, what is the probability of getting exactly 2 heads? So the first thing I want to do is identify what is my actual binomial distribution. So I have a binomial distribution because we know flipping coins counts for it. The first number you want to put in your parentheses is the number of trials. So in this case, we are doing 3 coins. Then after the comma, you want to write in what's the percent chance of any success when flipping a coin. Well, in this case, it's pretty easy, 0.5, 50%. Either heads or tails, it really doesn't matter in this case. So we're going to say in this case, X is going to represent, you don't have to write this down when you do these problems, but just as a reminder, X is going to represent the number of heads you would get when flipping this. So that's the success rate I'm using right there. Because sometimes they're going to be different and we need to pay attention to what this success rate is actually telling us. All right, we want to know the probability that our number of heads is exactly 2. So if I flip the coin 3 times, what's the chance I get 2 heads? It's essentially what this question is asking. Does that kind of make sense? All right, so if we use the formula, if we go the long way, we know our n is 3. In this case, we know our x is going to be equal to 2 because that's what we're looking for. So we can figure out this number in the calculator using that probability program. And then we can start plugging everything else into here, multiply it all out, and we'll get our answer. So start with the first part. It's going to be 3C2. So basically, before I do anything, I want the calculator to tell me how many different ways can I make groups of 2 from 3 things. So this is where you go to math, go over to probability, go down to option 3. And then it's going to have your 2 little boxes. We've done this before. So 3 goes there, 2 goes there, press enter. There are 3 different ways for you to make groups of 2 out of 3 items. Okay, first 2, last 2, and then the end 2. That's the 3 different ways you can do it. So we know the first number in our equation is going to be 3. All right, so all of this just gets substituted as the number 3. Are we okay how I got there? All right, this right here is your success rate. This P here stands for your percentage. That's this number right here. So this number 3 is going to be times by 0.5. And then how many of those successes do we want? Well, we're flipping 3 coins. We want 2 of them to be heads. So my exponent is going to match what my probability statement says. I have a 50% chance of getting heads. I want 2 of them, 0.5, 0.5. Then parentheses again, this is saying you want the complement of this percentage. So 1 minus 0.5, in this case, happens to be 0.5. This represents your failure rate. So if it doesn't flip to heads, everything else that's left over is the other result. In this case, it's tails, and we know it's 50-50, so that makes sense. Both of these percentages in your formula, if you're curious, should equal 1. So if this is 0.3, then this has to be 0.7. This is 0.2, this has to be 0.8. This is 0.65, this has to be 0.35. Doesn't matter, but they should equal 1 because you've got a failure and a success rate, and they need to equal the same, the whole solution. Now, the exponent up here is the number of trials you did minus how many successes you wanted. So we did 3 trials. That's our n. And we're going to take away the 2 successes, so we're left with 1. These 2 numbers should be equal to your n value. Because if you have 2 doing what you want, then that means you have 1 coin doing what you don't want. If I had 15 trials and I picked 7 successes, then I better have 8 failures. Because I want exactly this number. Does that make sense? So we got to think in terms of black and white now, which I know the world doesn't like, but that's what we're looking at. All right, so you can multiply all of these straight across in the calculator. Again, I'm showing you guys the long way, but just so you kind of know what's going on behind the scenes. 3 times 0.5 to the second power times 0.5. I don't have to do it to the first power. It's the same thing. There's my answer. Man, everybody's excited in class. All right. 0.375. Now, if you're doing one of these problems, these are the 3 things I need. Your distribution, your probability statement, your answer. This is optional. So what this tells us is if Mr. G is going to flip 3 coins, he has a 37.5% chance of getting 2 heads in any combination, because that took care of all the possible outcomes. All right, so does that kind of make sense what we're doing behind the scenes? All right, I'm gonna let you guys try one here. Example number 2, and then we'll show you a really long way to do a inequality, because you don't always have to do exactly. And then we get to play with the calculator program, which makes life go very fast and easy. All right, so let me catch up the slides here. There's the notes, just what we did. All right, 3, 0.5, exactly 2, fill everything in. Boop, there's our answer. All right, so answer just the first question only. Don't worry about the second question just yet. I didn't show you the inequalities. So the number of inaccurate gauges in a group of 4 is a binomial random variable. So they already told us you're good to go. If the probability of a defective gauge is 0.1, what's the probability that only 1 is defective? Go, see what you get. And remember, you need your 3 things: the binomial statement, the probability statement, and then your answer. Maddie, she didn't, oh, never mind. Dr., did I spell it right? McVee, M-C-V-E. M-C-V-E-E, right? Oh, McBee, not McVee. Gotcha. That's probably why she's like, who are you talking about? Because she works with all those people, so I love to hear her complain. You had who? Okay, I can ask her that too. Because Matthew, you took World Lit from my wife, right? Okay. She teaches a little bit of everything, so. This has been a weird year that both of us have had probably a good 12 to 15 students that we have in common. Last year was like 2. So. Yeah, everything's always switching again. However, I will say good news, not that it matters to you seniors, but good news is she's going to transfer, it seems, to the dual credit center only and not have to deal with the regular Plano stuff anymore. She was a little worried about it, but both her and I agreed the quality of student that comes through there is way better than the average student that goes through the Plano campus. You guys do a lot better job of actually trying to do work than some 26-year-old who's like, I think I'm gonna go take some extra English again. Well, I think they were making her do one thing in person versus online, or vice versa. I can't remember. She was all worried about it, and then they settled in and redid it to the way she was happy. So, all right, so let's see what you guys got going here. Again, it's okay if you make mistakes. Nobody's gonna know but you unless you share with them. So we know our binomial distribution is this format here. We have 4 trials at a 1% success rate. Now, what's weird, don't let your brain hurt too much on this. What's weird is our success is actually the failure of the device this time. So don't get too caught up in, oh wait, Mr. G, a defectiveness means a failure. As far as probability is concerned, we notice it as a success when it becomes defective because we identified it. Does that make more sense? So I know the word some of us will look at it and be like, wait, that's success, but don't worry about it. 0.1 is our success rate, which represents the failure of these devices. So we want to know the probability that 1 breaks. So if you go to your formula, then you know it's going to be 4 over 1, right? Which we know is going to be the same as 4C1. And then you're going to have your percentage, which is 0.1 success rate. And then for your X value, how many of these do we want? 1 of them. And then times our complement to this. So it's 1 minus P, which is going to be a 90% failure rate, which means it doesn't fail. And how many of those we want? Well, we want 4 minus 1, which is 3. So again, this should be your total number for N, and this should be 1 if you did everything correctly. Just as a quick way to go, am I doing this right? Because again, binomial, 1 or the other. So we go ahead and figure all this fun stuff out. So how many different ways can I do a group of 1 from 4 things? So we've got probability, math, 4, 1. Oh, there's 4. That makes sense, right? So we got 4 different ways this is going to happen because device 1, device 2, device 3, or device 4. 0.1 to the 1 power is 0.1. And then 0.9 to the 3rd power gives me 0.729. So I can go ahead and multiply all those up. So times 0.1 and times 4. And there's my final answer, 2916. Is that what you guys got? Good. Now, again, this is the lengthy way. This is like probably the last time, maybe one more time that you're going to have to do it like this. You guys kind of know what's going on behind the scenes and things are getting kind of set up. So I just kind of did my multiplication here and I'm good to go. So there are 4 different ways that this probability right here is going to happen. And you guys can think of it of like how we used to do the ones last unit, right? We just wrote them out like this. All right, I'd ask Matthew, what's the chance that one of my devices fails? So he goes, well, 0.1, and then the 3 don't. And then he's like, but there's 4 of these, so I times it by 4. There it is right there. So it's the same thing. So we're not really doing anything new other than the format that we're doing. So rest assured, you guys already kind of know this stuff. All right.
Mr. G.
Yeah, what's up, man?
So the part that has the B and then the parentheses,
Yes.
it's N and P, right?
Yes, sir. So it's always B parentheses, whatever your trials are, and then your percentage.
Okay.
Yeah, so for full credit, you need this, and you need your answer. Those are the 3 things you need. So after I show you the calculator, I'll show you exactly what it looks like on the screen. But yes, you need this, and this for full credit. All this other stuff in between, it's up to you if you want it. I don't really care. Like I said, you can.
Okay. Oh, I was putting in the wrong variable for the P because I got confused with the P parentheses X and I kept thinking that was the P instead.
Gotcha. Okay.
My bad. All right, thanks.
Yeah, you bet. Okay, so for the next one, the probability is asking for more than 1 is defective. So in reality, we're asking for that. So what is the probability that more than 1 is broken? Well, if you remember that we are dealing with a discrete distribution, we have this table. What are all of the possible outcomes that I have as far as these things breaking? I have 0, everything's good. I got 1, I got 2, I got 3, and unfortunately, all 4 of them broke. That's it. Those are the only possible outcomes I have for this experiment. Not 5, not 12, not less than 0. Either they all work or they all don't, or something in between. So if I want this, what I'm really asking for is the answer to this plus this plus this. Now, what I can do is add all 3 of those up individually and get the answer. It's way more tedious than it needs to be, but that is one way to do it. You could sit there and do probability x equals 2 plus probability x equals 3 plus probability x equals 4. Add them all up, you're good to go. Another way that's a smidge easier is to just do 1 minus and then take away the 1 things you don't care about. I don't care about these 2. So I can do 1 minus the probability x equals 0 plus the probability of x equals 1. So if I subtract those 2 from 100% of everything, those get taken away. What's left? What I care about. The reason why this is a little bit easier is because we already know this answer. And now all we have to do is find out 1 more and we're all set. So that's really the only reason it's easier, but you can do it either way and still get the same answer. I'm not going to show you the other way because it takes longer. So let's really quick figure out what the probability that x equals 0. So that's going to be 4 choose 0. So math, probability, I almost did it with the program and the calculator. You guys would have been like, what are you doing? So 4 choose 0. So how many ways can I choose a group of 0 out of 4 people? That's it, 1 way. And then we know that our percentage rate here, and let me actually write this out so you guys can see it. So we have 4 choose 0, and then we're going to have in our parentheses 0.1. What's the exponent going to be for this one? It's going to be 0, right? Because we want 0 of those failures. Times, what's the complement? 0.9. And then this exponent here is n minus x. Well, if I have 4 trials and I take away 0, I'm going to have 4 of those, right? So basically, I'm asking what is 0.9 times 0.9 times 0.9 times 0.9. Now, there's only one way to do that. So this is 1 for this number. What is anything raised to the 0 exponent? Oh, I'm sorry, man. I apologize. It's okay. Stop me. I apologize. This is why I teach math, not English. So what is anything raised to the 0 power? 1. Very good. I do like that Lauren called me out, though. So you guys always get nervous. And then we just got to figure out what 0.9 to the 4 is. And so this is going to be 0.6561. Well, we already know the answer then because 1 times that is just going to be that. So that's the answer here, 6561. So we can do 1 minus those 2 numbers, 0.6561, plus the one we got earlier, which is 2916. Everybody okay so far? My C's look better, Lauren? Thank you. And then my final answer for this whole thing, probability that X is greater than 1, I'm running out of space, that's why it looks ugly, is 0.0523. So there's my answer. There's my binomial statement, and then there's my probability statement right there. Again, more tedious than you guys are going to spend at any time doing this, but now you kind of know how the inequalities work, because remember, we're still doing a discrete distribution. So in the background, this table always exists for all of our things. So X has to be restricted to one of these numbers. X can't be 0.5. X can't be 1.673431. Like, it's either 1 or it's 2. Pick one. What you gonna say, Matthias?
Mr. G, so why'd you pull out the 0.9?
The 0.9 is the complement of 0.1. So remember, these two things have to be 100% because you've either got a defective or working device.
Oh, the 1 minus P. Okay.
The 1 minus P. Yes, sir. So I just didn't write that steps, but yeah, that's from this up here. Very good.
Oh, no. Yeah. Okay. All right.
All right. If my C's look bad, I won't say that. Wow. You guys missed it. I mean, it went perfect, all nothing, net. Just kidding. Okay. Do what? Hey, I'm just glad I didn't hit the roof. That was the part I was impressed with. Normally I hit the roof. Okay, so let's look at the slides real quick so that Lauren can see what the numbers look like without my crazy C's. Thank you, Lauren. Again, the slides aren't bad. They just don't really show what's going on as far as the calculations and the steps. So I'm just trying to give you guys an idea, because you never know the question that might come up and say, hey, Matthew, why do we use this formula? And he went, oh, geez, I don't know. I just type stuff in the calculator. Now he knows. And if he doesn't know, then it's on him because I showed. All right, let's use the magic calculator for all of its goodness and look at the shortcut for the calculator. There are two functions in your calculator that are going to be our best friend this unit and next unit. There's a binomial PDF and a binomial CDF function in your calculator. I'm going to show you where they're at. You use the PDF version, the top one, when you're trying to find a single binomial probability statement. So an equal sign is in your statement. This is the one you want. Probability X equals 1, 3, 7, whatever. You're looking for a specific amount of trials. That's it. Nothing more, nothing less. You can use binomial CDF for a cumulative probability from 0 all the way up to the number you give it. Now, the program is limited to only going less than. You can't go in there and say, you know, hey, I want to do more than. It's not going to do it for you. So you're going to have to be a little creative if you want, like our last problem where it said X is greater than 1. And it's not really that difficult, but we just have to use our brains for half a second, figure out, okay, what really are we trying to solve for? But if it's equals, it's easy. PDF, type in your stuff, press enter, it's done. Now, some people were asking on Zoom, what are the things that I need to show to receive full credit? Because Mr. G, if you're telling me there's a calculator, this gives me an answer. What do I need to show you? You need to show me this statement here. I need to know that it's binomial and what the N and the P are. Gotta have it. You can write it like this if it makes you feel better, but this is what I need. You need to have the probability statement and the equivalent answer that goes with it. So really, this is the format I want to see right here. I'll circle it in red so you guys can see it. I need that. You don't have to hear the example part, but I just need that. So this tells me right here that I have a binomial distribution with trials of 8 at a 30% success rate. You calculated that X was less than or equal to 3 at 80.6% of the time. Yes, this can only be less than or equal to in here or equals. Now, we can solve for greater than or equal to, but the calculator will not. We'll have to be creative on how we do that. Does that make sense? Yeah, we're not limited to only solving these. We just have to understand the calculator has programming limitations. You don't need to write out all of your calculator notation. You're going to see it on some of the note slides. I put it there because some of us have the old 83, 84 fat ones, and they look a little different than our nice ones we're using in class. So they will still work. I'm not making fun of them. Just letting you know that your notation, it won't be a nice menu option like you see with ours. You also don't need to show the equation unless Matthew's just super excited to write out that equation over and over again, which I know he is. But no, you don't have to show me the equation. I just need the binomial, the probability statement, the answer. That's it. And that's all AP needs too. So it's not just me. Okay, let's practice one with the calculator now. So a generic trait of one family manifests itself in 25% of offspring. If 8 offspring are randomly selected, find the probability that the trait will appear in exactly 3 of them and at least 5 of them. So first thing I'm going to do, I'm going to write B parentheses, and I'll show you on the screen here in just a second. What is the N on this one? 8. 8 randomly selected offspring. 3 is going to be our X value because we're going to test this thing. Parentheses, what is our percentage success rate? 0.25, right? Convert your percentage to a decimal. So the first statement we want to solve is the probability of X is equal to, because it says exactly, 3. The second one we want to find out is the probability that X is at least 5, which is greater than or equal to 5, which we already know the calculator won't do that, but we'll figure it out. All right, camera mode. I don't think there's any C's this time, so you should be okay. All right, so hit second, hit vars. So you want to write a note in your notes where to find these things. Second button, vars button. Oops, hit the second first, Mr. G. There we go. There are a ton of different things in here that we could use at any given time. The binomial ones are at the bottom, so it's actually quicker if you hit the up arrow to get to them. You hit the down arrow, you're going to have to go through 0 through 9, and then it finally gets to where you're looking at. So there they are right there, A and B on my calculator. They might be different on your guys' at home. I don't know what yours looks like. But binom PDF is the one when we're going to use first because that's equals. And binom CDF is what we're going to use for this one because that's the cumulative one for less than or equal to. So let's do option A, binomial PDF for the first one. This thing is gloriously nice. If you don't have the nice menu option like this, I'll show you what yours will look like in a second. How many trials did we have in this experiment? 8. This is why it's important you guys write this stuff, not just to be tedious. What is the percentage success rate? 0.25. What X value do we give a flip about? 3. Everybody see that? So 8 for N, 0.25 for the P, 3 for the X value. All right, for those of you guys with the, I'll press enter in a second, you guys can see the answer. For those of you guys with the bigger, wider TI 83s, 84s, when you hit that function, it's going to show binomial PDF with just an open parentheses. So what you're going to want to do is type in 8, 0.25, 3. Then you can use your older calculator if you don't have that menu that I have. If you have the menu, you're fine, but if you don't, then that's what you're going to do. Yes, ma'am. So second vars, and it's near the bottom. So it's like A, B, somewhere in there like that. But usually what happens, Maddie, is that all it'll show you is usually just this, like with the little parentheses like that. And so then I'd go down here, I'd press 8 because it wants your N first, and then there's a comma button. And then it wants your P second, so 0.25, and then comma, and then your X value. So it still works exactly the same. You're just gonna have to be a little bit more computer programming with it. Press enter, you're done. That's your answer, baby. 0.2076. So without doing any work in an equation, Matthew knows that with this family of 8 and a 25% chance of getting a genetic trait, exactly 3 of them have a 20%, 0.76, whatever chance of getting it done. Yay, technology. This is all you guys got to do. So all that other stuff is just so you know how it works. All right, for this one here, probability that X is greater than or equal to 5. Problem is, all we can do is less than or equal, so we got to fix it. So again, really fast, just so you guys can see visually how my brain looks. This is our little number line of distributions, right? These are my only outcomes for X, all right? And then underneath it is the probability of each of those, right? So if I want greater than or equal to 5, I want that section. The calculator is only going to do predictions going this way. So if we take away all of these, guess what we're going to be left with? The section we want. So we're going to rewrite these as the probability that X is less than or equal to, well, what's the highest number I get to before I want to cut it off? 4. And then we're going to do 1 minus that. So this, if you write it as this, gives you the same answer. So for those that don't want to draw the number line every time, the trick is, if you're going in this direction, take away 1 number, and you're good to go the other direction. Now you have to watch carefully. All right, this goes back to your algebra days. Watch, some of these have equal to, some of them do not. So you have to keep that in mind. So if this didn't have the equal sign, if it said greater than 5, then this would be 5. Because we want everything bigger than 5. Does that make sense? So just watch carefully. Those will sneak up on you. All right, so let's figure out this number in the calculator and then just subtract it from 1. All right, so second, vars. Again, I hit the up arrow. This time we want to use option B, the CDF, because we're using a cumulative probability. We want to know all those values below 4. All right, trials still remain the same. We're still at 8. Percentage remains the same. It's still 0.25. X value in this one is what you see. It's 4. So this on this one tells the calculator 4, 3, 2, 1, 0. All right, you go to paste. again, those of you guys with the wide or older calculators, it'll still do the same thing as before. It'll open up with the parentheses. You just got to type in 8, 0.25, 4. All right, press enter. Now, don't write this down as your answer because it's 1 minus this answer. Please remember our rounding rules. Don't start rounding yet and get excited. So just do 1 minus, and then you can press the up arrow to copy and paste on these nice calculators. Press enter, and then you get the exact answer you want. Now you can round. So our final answer here for this one is 0.0273. Ta-da! Again, all I need is that, the original statement, and this right here. Everything else is gravy. All right, what do you guys think? Question?
Does that 1 minus and then flipping the thing always work in that situation?
Yes, it does. The only thing you're gonna have to watch out for, Matthias, is this symbol here. If it was this instead, just for hypothetical funsies, okay, if it's this, then it's really gonna be equal to this. Because this means more than 5, so that means everything 5 or below goes away. This one means including 5, so everything 4 and below goes away. So you see the difference there?
Okay. Yeah.
So just watch your symbol, and as long as you're comfortable with the difference in the symbols, yes, it'll always work.
Okay, all right, thanks.
Okay, give me just a second. I'll come over and look at yours. I'm gonna let them do some practice, and we can look at yours in a second, man. Okay, so now you guys got an idea how the calculator works, and you got the examples or the answers for example number 3. All right, let me put them on the screen real quick. I will let you guys play with the beginning of number 4, and then we'll talk about how to do average and standard deviation, and we're done. All right, so there's my answers for the last one. If you guys need to see them again, there they are. All right, again, you don't have to write this step right here. It is there for your guys' reference, but if you have the older calculators, this is what yours should look like when you're typing it in. All right, so try this one. There are 2 questions you can give a try on this one in your notes. So we got 30% of voters in a particular county are Republican. If 10 voters are selected at random, find the probability that no more than 6 of them will be Republicans. And you can do the next question. At least 7 are not Republicans. So we'll see how many of you guys have got this stuff really figured out. Kate's eyes are already spinning the circle. Figured it out. Oh, so yours has the menu. Okay. Have we updated yours? There's a way to do an update on yours with this one. At the end of class, I have the core. We try to see if there's an update.
Is there like, so are we assuming we're just doing?
No, you're choosing between Republican and not.
Oh, okay.
So the other ones would be libertarian, atheists, satanic. I don't know, just make that. Green Party, whatever else. So yeah, be careful on these problems. Remember our, and Lauren brings up a good point and I didn't talk about it yet. Remember when we did our Venn diagrams and you guys struggled with the question that said, you know, how many children don't like broccoli? And you guys went, oh, that must mean the apple's children. No, remember, don't like broccoli just means not broccoli. So if broccoli was 26% favored, then what's left over is not broccoli. So think of it more like that. Don't think of it as I'm looking for the opposite, because we're all trained that opposite of Republican is Democrat and vice versa. For the first one or second one? First one, yeah, it should be. The second one depends on how you want to solve it. There's 2 ways. It can be or it doesn't have to be. Excuse me. And I'll go over both in a second. There we go. Voice is warming back up. And again, remember, you only have to show those 3 steps to get full credit. Unless you want to write out other stuff, then go for it. Nobody's going to stop you. I mean, most of our things are going to be on Canvas anyways when it comes to quizzes and tests. So just know what we're looking for. Figured out number 2 yet, Kate? I remember I just told her not Republicans in her eyes did this real quick. She's like, all right, what's my binomial? She doesn't know who that is, Betty. She must be somebody that she hadn't worked with or different. Okay, so we can look at number one while you guys finish up the crazy one. And it's not really that crazy, but it's different. So number one says, what is the probability that, I'm trying to look where it is phrased in here. We find no more than 6 to be Republican. So we know this is our binomial distribution. There's 10 of them, 30% chance that any one of them is Republican. So we want to find the probability that, I just read it there, no more than 6 will be Republican. So X is less than or equal to 6. So it could be 0, it could be 1, it could be 2, it could be 3, it could be whatever, as long as it's not more than 6. So this one's nice. So you just type this one into the calculator and you're all set. So this is second, vars, go down to the letter B because we're doing a cumulative. Make sure you type in all your correct information, 10 trials, 30% chance, and we want to know 6 or less, and we're good to go. There's your answer. So this one's going to be 0.9894. What you got, Derek? So on this one, the question was asking, what was the actual phrase of it? At least 5. So this one was saying at 5 or bigger. The problem is our programming in the calculator is limited to only doing it like this. So if I typed a 5 in for this one on this particular problem and didn't switch or fix anything, what it would have figured out for me was 5, 4, 3, 2, 1, 0. But what I really wanted was 5, 6, 7, or 8. When it's presented like this way, you're good to go because your calculator is built for this one. So yeah, you don't have to be fancy with this, and not every equality needs to be fixed, and that will be kind of a tricky thing to watch out for. When do I need to fix them? When do I not? This one said at most or no more than 6, so that means the maximum number is 6. So we're okay with 6, 5, 4. So we're going in the right direction, and that's what the calculator, it always goes from 0 to up to the number you put it for X. It's never going to go from that number or higher. So, all right. So number one, hopefully everybody did okay. Any questions on that one? I'll let you guys play with the calculator by yourself. Okay. Number 2. How many Republicans, what is the probability at least 7 are not Republicans? So there's 2 ways to solve this, and you're going to get the same answer either way. I don't care. So Mr. G's brain looks at that and says, okay, we're now looking for not Republicans. So what I did on mine for the first time is I switched by binomial distribution to this because this is Republican, this is not Republican. And then I went ahead and solved it and said, okay, it wants to know the probability that X is greater than or equal to 7. Because the question states at least 7 are not Republican, which is going to be that percentage. So that's my new success rate. You can do that if you want, because you only have one or the other option. Does that make sense? So then when it's in this format, I solved it as 1 minus the probability that X is less than or equal to 6 now. So in the calculator, I just figure out this one at this percentage rate and subtract it from 1. So second, vars, option number B or letter B. All right, trials are still 10, but my percentage rate has to change because not Republican is 70%, Republican is 30%. And then on this one, we want 6, which it's already set up for. Press enter, and then it's 1 minus this answer. Because I want to take away everything lower, because like Derek just asked, how do we do when it's higher? We got to subtract out the lower stuff. What's left over is the higher. So this is 0.6496. That's one way to solve it, not the only way. That's just the way I solved it first. The second way to solve it, and you guys can decide which way you want to do it, and you might even have a third way, it doesn't matter. The second way is just to keep things like they were. So I have my binomial distribution at 10 and 0.3. And then just be a little creative in your brain and go, okay, if I want at least 7 that are not Republican, then what's the maximum number of Republicans I'm allowed in order to make sure that that is the rule, if there's 10 total? 3. So really what I want is the probability that Republicans are equal to or less than 3. These are the same thing. Because if I want at least 7, then I can't have any more than 3. Excuse me. And so in the calculator, I can go ahead and solve it this way. This requires no flipping of inequalities, no changing of stuff. So in reality, this is probably easier, but it doesn't work with my brain as well. So I did it the first way. So this is now going to be second vars, again, binomial CDF, 10 trials. I'm back to my original 30%. I haven't changed anything. Everything's good to go. But I know if I want at least 7 not Republicans, then that means at most I'm going to have 3. Excuse me. And then lo and behold, there's our same answer. So 0.6496. So no matter which way you do it, I'm not going to know. You're going to get the same answer either way. All right, let me get my stuff out of the way so you guys can see option A or option B. So this is the way I did it because my brain is weird. When it says not Republicans, that's what I'm hunting for. A lot of you guys are smarter than me. So you could probably just in your brain go, duh, Mr. G. If I want 7 nons, then that means I'm only gonna have 3 is. And then no. Happy hunting. Go whichever direction you like. Or do a third option if you got some other way that works. As long as you got this number, I'm happy. Because remember, this is all you need to show, this right here. Or this is all you need to show, this right here. We cool? All right, last thing we're going to talk about then today is average and standard deviation. Calculating them individually, easy. Doing the last problem might make some of our brains hurt. All right, so for average and standard deviation, you have some formulas to help you out with these things. Let me put my answers up here. There we go. There's both of them if you want to see them. All right. Here are your 2 formulas for average and standard deviation. For the average, it's easy. You take the number of trials times the percentage. And these formulas are at the top of your notes page here if you want to like write anything down. Standard deviation, also very easy. Take the number of trials times the proportion times its complement and then square root of it. Nothing fancy. We don't need to do variance and all that weird stuff we did the other day. Just type these babies into the calculator. It works every time. All right, so our 2 questions with these are, how many Republicans would I expect out of 10? And what is the standard deviation for this distribution? So that phrase right here, would you expect? That means, what is the average? So if I got 10 peeps from this county, and I know 30% of them are Republicans, how many do I expect to be in that 10 to be Republican? So we're going to just use the formulas, and that'll be our answer. So for the average, again, here's my binomial distribution if I need to remind myself of anything. The average is N times P. So my N is 10, that, and there's my answer. Which makes sense, right? If I had 10 people in a room and everything being equal, I would expect about 3 Republicans in it from this county. Standard deviation, same kind of idea. Underneath the square root, you're going to take these 2 numbers, so 10 and 0.3 again, and then just add in its complement. So number of trials times the percentage times its complement. And then this one might need a little bit extra. So what do we got? Second square root, and then we've got 10 times 0.3 times 0.7. There we go. There's our answer. So again, this is not meant to be tricky. You guys should be able to find these fairly straightforward. So 1.4491. Now, with these, because you're now actually talking about individuals, you need to say like voters or whatever. So in this case, that's what they use for the title. So don't forget your labels on these things because these are actual numbers now, not percentages. So I would expect 3 voters with a standard deviation of 1.4491. Now, where our head starts to get a little bit crazy is, remember, we're dealing with discrete. So in reality, this standard deviation is a little misleading because I'm either going to have a voter or I'm not. So this is the actual spread of the data, the actual value for it, but I'm never going to have 1.4491 voters. And what's the guy coming in with like a left arm and a right leg and like half an arm? Like, all right, we're not, it's a person. Okay, so they're either a person or they're not. So that's what makes this last example tricky. What's the probability the number of Republicans out of 10 is within 1 standard deviation of the mean? So it starts off fairly easy, and then it gets to the point where you have to stop and think about it for a second. So again, I just get in the habit of doing this to remind ourselves what we got going on. We're simply going to take the average and add and subtract this number to it. All right, so we're going to do 3 plus this number and 3 minus this number. So what is 3 minus the number? 3 minus 1.4491 gives me 1.5509. And then for the addition, it's 3 plus 1.4491. Don't need that extra there. So I get 4.4491. Okay, let's make sure I did it right. All right, so when we're trying to find the probability of one standard deviation from the mean or one standard deviation from the average, this is the numbers that we're looking at. So we essentially want to know the probability that the number of Republicans I have is between this number and this number. Now, here's the problem. I can't type this into my equation. I can't type in 1.5509. This is discrete. Either you have one voter or you have two. Same thing over here. I can't type this into my calculator. Either I have 4 voters or I have 5. So this is where you have to get visual for a second. We have a number line. All right. I'm standing at 3. That's my average. Going this way is 2, 1, and 0. Going this way is 4, 5, 6, 7, 8, 9, and 10. So basically, I want to know from this point right here, where am I limiting my cells? Because these are the only options I have for X in my trial. Typically, what we would do as math students is we would just round it to the closest whole number. Sometimes that works, but we got to be careful because we can't go over these numbers in these directions. So if I'm standing here at 3, okay, this is 3 right here. What's the closest whole number I can get to this without going past it this direction? 2. So in this case, rounding it would have been okay, but just so you guys know, that's not always the case. So I can put 2 here because that's the closest whole number I can get to 1.5509 without going on the other side of it. I don't want a number back here. Same thing going the other direction. If this is 3 and I'm going this way on the number line, what's the closest I can get to this number without tripping over it and going past it? 4. So that's that number right there. So now this becomes like this, and we can solve it. One thing to keep in mind, for example, I'm not saying this problem has this, but for example, in case you guys run into this later, let's say same type of problem scenario, but for some reason I got this as my number here. All right, this is not going to be 1. This is still going to be 2. Why, Mr. G? This rounds very close to 1. Wouldn't it be more accurate to do that? No, the way this is set up, you can only go in this direction up to this number without going over. So 1 would be too far. And this is where some of you guys who are pure math students who are really smart and understand how numbers work are going to have your brain hurt because you're like, this should be 1, Mr. G. It's right there, but it's not close enough. So this is a 2. Same thing here. Your brain's going to be like, oh, that's just 5. Nope, 5's too far because 4.68 is as close as I can go this way. So this would also be the same thing. Don't ask the reason or why that it does it. Just trust me. That's how you solve it. All right, so just be aware of that. Most of the time, rounding it is okay, but don't round this to 5 and round this to 1 and say, oh, now I got it solved. That's wrong. Somebody always does it. Don't be that person. Okay, so let's solve this. What are we actually asking for? We're asking for this percentage here inside our number line. We want to know between 2 and 4. So we don't want anything here, and we don't want anything here. Or our calculator only lets us go to the left. So if I start off with the big number, probability of X is less than or equal to 4, that takes care of everything from here backwards. So that's good. We've already eliminated all this stuff. Now we need to trim off that last little bit right here. We need to get rid of this stuff. So we're going to minus the probability that X is less than or equal to, what's the first number I want to get rid of here? 1. So this translates into this in my calculator. Probability of X less than or equal to 4, that's everything this way, minus this extra stuff here after the 2. So some tricks for people that want to do it without doing the number line every time. Closest whole number without going over, so 2 and 4. Then 4 goes first because it's the biggest, and then 1 less here. All right, for those of you guys that don't want to have to draw this, but draw it if you need to. All right, so we're going to do 2 different probabilities at the same time and subtract from each other. So I'm going to do the 4 first. So second, vars. All these are going to be CDF because they are inequalities. Same percentage as before, 10.3. First X value is 4. Here's my first number. And then do it one more time with 1. Don't forget it's still the second vars and the CDF. Don't do anything else. So it's still 10, still 0.3. This is 1 now. Here's my 2 numbers. Don't forget to subtract them. So don't round anything. Just copy, minus, copy, enter. So there's your final answer, 0.7004. All right, so I got my probability statement, my thing, and my answer, and I'm all good to go. The rest of it's just there if you guys want to write it down or don't write it down. Now you know how to do all these things. Questions for me?
I have 2 questions.
Ask Mr. Matthias. I love your questions.
So, for like, as far as showing work, do you want us to, what's it called? Do you want us to, for like the P and then parentheses, do you want us to show the, like the X minus, the other one, or do you want us to show the first one with the original numbers?
All you need to do is probably on this one, if you're talking about this particular problem, is it would be in your best benefit to show me this just so I know you did the adding and subtracting of the standard deviation correctly.
Okay.
And then I would just do this one and then you're done. You don't have to do this if you don't want to.
Okay. We don't have to show the minus the other one?
No,
then?
I don't need to see the minus thing. So if you write it as that, then I'll know you smartly went from here to here and then I'll know your answer is correct.
Okay.
Yeah.
Um,
Because your answer here will tell me if you did this part at all.
okay. Yeah, that makes sense.
Okay.
All right. And then my second question is on example 3, when we did at least 5,
Okay.
it was a greater sign or greater than or equal to sign, right?
Yes.
It was X is greater than or equal to 5.
Yes.
Why, when we did the part 2 on example 4, where if you were to go what's it called? If you were to do the one where you have the 0.7, wouldn't that, or no, sorry. If you do the one with the 0.3, it says at least 7. So why isn't that a greater than or equal to sign?
It is. I put it on there as at least 7.
Oh, it is?
Yeah.
What?
So if you do the first method, there was 2 methods on there. If you do the first method, it was the binomial was 10.7. And I said to make sure at least 7 are not Republican, it was the probability of X is greater than or equal to 7.
Oh, okay.
It does translate to 1 minus P X less than or equal to 6. So that
6.
becomes that one.
Okay.
If you did the second method, you left it at 10.3, but then the probability statement was easier because if you wanted at least 7, then
It's less than
is 3.
or equal to. Okay. All right. Thank you.
So maybe I just wrote it weird because my C's apparently look bad too. So maybe I just missed it.
No, it's okay. Thank you.
Yeah, no problem, man. Could you please show how you got the 15509 and the 4491 again? Yeah, you bet. So when you start this problem here at the bottom, it's asking you for 1 standard deviation away from the mean. So what was the mean earlier in the problem that we looked at? So our average was 3 because we got that from the number of trials times 0.3. So that's where this came from. Now, in order to find 1 standard deviation from the mean, you add and subtract the standard deviation to those 2 numbers. So the probability that, all right, what is 3 minus, and our standard deviation was 1.4491. So that's the first number that goes there because you're going backwards, something smaller. So that became the 1.5509. X is in the middle because you're going plus or minus a standard deviation away from the mean. So now you're going to add it. So it's 3 plus 1.4491. Again, this is what my standard deviation was. And then when I do that, I got 4.4491. So that's where those numbers came from. Yeah, no problem. And just remember, you can't type this into the calculator because this is discrete. Now, if this is a continuous distribution, then we're good. We're done. Continuous can have decimals like that. We'll talk more about that when we get to them. But for discrete, it's either a voter or it's not. There's no like point, hey, he's kind of like a mixed, most days he's Republican, some days he's or whatever. When you go cast your vote, you pick one. Okay. Any other questions? So what are the action items for you guys then? Pretty straightforward homework stuff. Where's my packet? There it is. So last time we did the bunco activity in those notes. If you guys got questions, hit me up with them. I'm happy to help. Today you add in 2 pages for binomial. There's a binomial here and a binomial here. Most of it's pretty much exactly from the notes. I can't really think of anything that we went over that's not going to be on here. So you get some good practice on that. And then the supplemental packet, I'm going to come around and pass that out to people I know. Hey, thanks, Mr. G. We love you so much on the weekend. You don't have to do it this weekend. It's not due like right away, but the first thing that's in the supplemental packet, look at it, binomial practice. So I know Lauren likes to just get these things done. So I was thinking of like her, you know, maybe she wants to do them before she forgets about them. And then she can turn it all off and worry about it later. All right. So if you're that kind of student, start on the supplemental packet. If you're not, wait till later, use it as a review. Just watch your due dates in the learning plan for when that's due and just make sure you get it turned in before then. But class, I'm going to give you guys your copy, and then the FRQs I'll give you guys sometime next week. Cool deal? All right. Thanks for being a victim to all my craziness. Hey, you're up. Just for you, man. Thank you. You want one of these? If you don't want one, just say no thanks. I'll turn it off. Want one, Lucas? Okay. Laura? Remember, no textbook requirements this unit. There if you want them. Not if you don't. Yeah, you're welcome. You're welcome, welcome. Here. Evidence of my failure. Yeah, just enough left over for Zoom period on Monday. See if Zoom people got any questions. Zoom people, if you guys are good, have a good weekend. If it snows this weekend, enjoy it. If it doesn't, remember, you live in Texas, you're not supposed to see snow. So I laughed last night because I got an update that says the probability of 4 to 8 inches moved up to 35%, and the probability of 1 to 4 inches moved up to 25%, which puts them both over half. And I laughed. I was like, that's not gonna happen. And then there was like a slim, like there was like a 5% chance of something over 8. I was like, if I ever see 8 inches or more of snow in this place, I'll know we're about to die.
Yeah.
The apocalypse is coming. I was like, I've lived here since 80. When did my parents move here? 87, 1987. And the most I've ever seen on the ground at once is like 4 inches in this location. I'm not saying ever. I've been up north where there's snow. You anxious to go? You still got 5 more minutes, girl. I'm already letting you guys out 15 minutes early. You can't get me in trouble. 5 more minutes.
Like, but I feel like because we have like Zoom and stuff now, I feel like they have to make everyone convertible.
I'm wondering if that's what will happen. If I get like an email Sunday night that's like, well, just go online and teach. I'm like,
Yeah, instead of not being.
well, it's my on level day and they're supposed to take a quiz, so I'll probably just pop in and be like, just take the quiz today. And I can mark off that well, that's good though, if you think about it. Because most of your teachers are going to be like me and they're not going to do anything special because they don't want to teach. And number 2, we don't have to make it up. So that's actually a win-win-win because we get snow, we get an easy day, and we don't have to make it up. That's what I'm saying. That's not a net. Yeah, she's going to be like, all right, we're going to see you later, Lauren. Make your way on over.